Welcome to the next installment of ground and introduction of radiation and DXing. Yes, this is a very important topic for many. DXing, distance, how to get that signal out. And we're going to show the relationship between at least one antenna and ground and what gets in the way. And this particular topic is called the Brewster angle. So I'm going to show you what everybody aspires to as far as a monopole. Here the radiating tower sits above a field of radials. This is a ground line, the horizon. And these red lines are the characteristic radiation pattern for a monopole, which is to say mostly in that or in that direction, of course, and all the way around. This structure is a donut. So think of this turning, returning, and coming into and going back to there. It's reference to this point. Now this is a far field experience. If you had a field strength meter out 10 wavelengths, roughly 10 wavelengths, this is the kind of, well, and you could fly overhead at a similar 10 wavelength separation. Your meter would give you a very high reading along this curve and then suddenly dip as it went overhead. This is the null. Continuing forward, that value would rise again and maintain its high value all the way out to the horizon. Now this is by virtue of this is a perfect ground kind of representation. But we don't have a perfect ground. We have radials that are trying to approximate a perfect ground. But this perfect ground is only in the proximity of the antenna, and not out at this 10 wavelength. So this is kind of a mixed representation of, say, a far field overlay in a near field representation. If we were to, as ground conditions vary, so does this radiation angle. And what happens is it modifies at these points here. Over less than perfect ground at the far field, we will exhibit something of this nature. Such that our best radiated takeoff angle is roughly, here, let me get another color, is on the order, and this is our reference point for the far field diagram. This would be our best takeoff angle, similarly over here as well. If we went below this angle here, we would only get about that much of signal out into the ether. So what happened to this line here? How did we go from a very nice hot signal in that at that close at that takeoff? That's about a 5-degree takeoff compared to about a 40-degree takeoff. Which would you prefer? That no doubt, but this is what you're going to get over various grounds. And then now we're going to look at some facts and figures to match this. And this takes us to this graph here. And this is labeled the pseudo-Brewster angles, frequency versus soil quality. We've discussed soil quality earlier. We've also used salt water as a reference, which is perfect. Fresh water, which is nearly so. So the salt water, the Brewster angle is, let's see, two degrees. A couple of degrees out to about, all through HF. Less than 2 degrees. So what does that mean in terms of my earlier drawing? Let's go back to that. This would say that this is better represented by something that looks like this. And our best launch angle has, by virtue of this, come down to here. So we've roughly halved formally now. So reconsidering this the pseudo-Brewster angles and soil quality, and here's the Brewster angle for salt water. We can see that it's not perfect, it's just, but it's nearly perfect. If we could get a takeoff angle down in the less than 5 degrees, and that's this point, which if you look at this is the freshwater Brewster angle of about, let's see, that's about 7 degrees. These two lines give us the best we could hope for in nature. The common ham experience is more along these lines, however. Each of these lines is progressively worse soil up all the way to this, very poor soil. And here we find that the Brewster angle, the pseudo-Brewster angle, varies from 0 to about 17.5 degrees at a very low frequency of 2 megahertz. Up here in the 80 meter band, it's as, well, 20 degrees takeoff angle from a vertical monopole over this kind of ground with a radial system, 20 degrees. If we were talking about 20 meters, poor ground is going to have something under 25 degree Brewster angle. So that's the highest, and that's the poorest angle actually of a takeoff, but it's available to you. Typically, the better numbers are going to be up higher here at 35 degree takeoff angles. As the frequency increases, you'll note that almost all these lines verge to one value. So use this as a reference for your propagation and how likely you're to get that dx and how many skips it's going to take, because all of these are all soil values in the far field, 10 wavelengths away from you. So, and here's this is all from work done by Seebeck, LB Seebeck, W4R and L. So a quick survey of the first principles of the monopole design, radials, the implications of the ground not only beneath it, but at a distance as well, and how that impacts your takeoff angle and DXing, because the lower the takeoff angle, the less skips to reach that dx. Or you may just wish to know where you're going to land at. Well, of course, when you do have a skip, you're coming back down to another ground, and that too is going to reflect at the same angle if it has similar soil or better soil properties than what you're planted on right now. So all these considerations are mixed into this short discussion. So I'm going to close it with that and say 73s.